Hello folks, this is video number 20 in a playlist which is devoted to motion design application in 3D experience. It's a kind of problem that you see in a dynamics textbook or a course, and what it deals with a bar which is falling under gravity as a free fall and hitting the floor. And what we like to do is a couple of things. One is to find the velocity of the mass center immediately after impact, mass center of that rod, and angular velocity of the body immediately after the collision. Now we have to know a bit more about this. For example, you're told that the coefficient of restitution for the impact is 1. In other words, it's a fully elastic impact, okay? And if you want to know the analytical solution to this problem, you can consult this reference. It's example 5.16. And it's not an elementary problem in a sense that to do it analytically, you have to apply the uh, impulse, linear impulse, linear momentum principle, and the angular impulse, angular momentum principle, and of course, together with the coefficient restitution being known. What I'm going to do when I solve this problem, I'll look at two cases. When the impact taking place is like that, flat, or it is curved. You see that the one on the right will give you results that are close to an analytical solution, and the one on the left will be different. Okay. All right. So when it comes to solving the problem analytically, or sorry, when it comes to solving the problem with motion design, I'm going to use these parameters, and there's no reason to simulate, for example, the free fall. So what I do is a relatively short duration until it hits the floor and bounces, and store the result for display purposes every so many seconds. Now, in order to do that, I have to know certain things. For example, what is this angle of inclination? For example, the distance from the tip of the bar all the way to the ground is h, and m and l are the length and the mass of the bar. If the coefficient of restitution is 1, you can we will actually this is with any coefficient of restitution. In that reference that I gave you, the velocity of center of mass is given by that expression. Of course, before the impact is going to be just square root of 2gh on free fall condition, and the angular velocity before the impact is 0, and after impact is going to be this expression. Now, the other thing is, if you assume that the coefficient of restitution is 1, here's the value of g. Assume that the length of the bar is 1 meter, radius of that tip. Actually, we're going to assume that the bar is cylindrical with radius 5 centimeter, and steel density is being used. And if you work this out from a height of 2 meters, you're going to get so with that information, the velocity of the center of mass after impact is 1.25 meter per second, still going down, of course. And the angular velocity is 21.26 rad per second. All right, now we're going to model this thing in a 3D experience. Okay, we are in the 3D experience interface, and I'm going to go to assembly design, which is basically a 3D experience CATIA. So first thing is insert a 3D part, and I'm going to call this thing rod properties, call it rod, and instance is rod, and the color that I'm going to use for making it is orange. And now we're going to make it. So double click on the 3D shape here. That'll put you in part design. On the vertical plane, I will sketch. I will sketch an axis because there will be a profile that's going to be shafted about this axis. One of them is going to create the one with a flat face. The other one is going to be creating the one with a curved face, curved surface at the end. So let's do the profile now. Here is the profile. Before I do that, let me see what the length of this axis is. So let me make that thing 1.2 for visual purposes. You'll see why right there. So there is the 1.2 because the length of the rod is actually 1 meter. So I made this thing 1.2 so that I can see it. So profile, it starts on the axis, make sure it's on the axis, and then I go vertically up, and then horizontally parallel to that shaft, and go vertically down so that I reach the axis. Okay, now a couple of things here. Let me dimension this thing to be 1. It's going to be the length of almost the length of the rod. There we are. And the reason I made this thing 1.2 because I wanted to see the rest of the axis, although it's not necessary. Now the length, this radius is 5 centimeters. So the radius of the cylinder is going to be 0.05 meter, which is 5 centimeter. Okay, a couple other things. The angle between the axis of this and the horizontal, horizontal axis is 45 degrees. So let's do that. So dimension between the axis and this horizontal thingy. Let's try it again. Axis and this horizontal axis. Where is the dimension? Dimension between that and the horizontal axis. This is 45. Should be 45. Okay, and I also want to lift this shaft, this thing up, so that the distance from this point to the horizontal axis is 2 meters. So another dimension here. Dimension between this point and this horizontal axis. It's 2 meters. 2 meters. Okay, it's way up there, right there. Okay, let me show you what happens when I exit and I shaft it. It creates this, yeah. The only thing is that this end, I also wanted to be able to make it round. So say cancel. Let's go back to that sketch. I'll show you how I'm going to approach this. I'm going to make an arc between the center of the arc is this point of intersection, and it goes like this, and it goes to the axis. Okay, hopefully this is coincident with that. If not, I'll make sure it is. So this point control that axis. I want to make sure that they're coincident with each other, because I'm not absolutely sure whether it is right now or not. So let's try it. Try it again. Yeah. Let me make this thing a little bit over there. Okay, notice that. Notice that. Yeah. Now I can go make it coincident. So this point this point, control that axis. I want them to be coincident. Now they are. Okay. Now notice that if I make this line, a construction line, and leave this thing as solid, when I exit, essentially I'm going to get, what is this? I'm going to get when I shaft it, I'm going to get the round end. Cancel. If I go back here and I make this thing solid and that construction line, see that? Exit, and I shaft it, it becomes a flat end. That's why I did that weird thing for sketch. Let me go back, make this construction for now, and this solid. Very good. Exit. And if I shaft it, I'm going to get my round end. Good. All right, let's go. While I'm here, by the way, I'm going to make the point at the center of mass of this object. So here's a point at the center of mass or center of gravity of this this piece. Center of gravity of this piece. Yep, it's just going to be right up there. It's made. There's a point right up there. You can see that. Very good. So we go all the way to the top. Insert the floor. Insert the new 3D part. I'm going to call this thing floor. Properties. I'm going to call this thing floor. And floor. This is the instance name. And for graphics, I use yellow. Okay, so let's go to the floor and make it. It's just basically a box. So on that plane, I will sketch. So for my floor, I make something like that. Exit. Okay, and we pad this. Flip the direction. I'll make it about 0.05 so that I can see it at least. There we are. So this rod is going to drop on that floor. Now, we go all the way to the top. Because the floor does not move, I might as well go to the assembly and fix it. Good, so that does not move. By the way, these planes I don't need, so I might as well hide them. Hide them. Okay, very good. Now, we are pretty much done as far as making the assembly is concerned. Now we're going to go to motion design, which is an application. Because there is no mechanism here, it's going to create it. It's called it mechanism, or called motion analysis case 1. Fine. Now let's see what happened here. First of all, there is the global branch. If you double click, gravity is always automatically imposed minus 9.1 in that direction. There are two bodies here. The rod, if you double click on it, notice that it's almost 63.06, which is right here. I think in the original, the first time I showed you this slide, this might have been 61. It should have been 63. But anyway, it is. So properties of steel are used, and so okay. The floor is stationary, although the properties of steel are used, but because it's fixed, it really doesn't matter what it is. I can use rigid massless if you want, but I'll leave it the way it is. Okay, now notice that a dynamic step has been created over 5 seconds. Let me make this thing less than 5 seconds. Let me make it about 0.7 seconds. There's a reason I want to show you that, 0.7. And we're going to come back and do something with these things later on. But right now, I made it 0.7. Okay. And we have to create the interaction or the contact between these objects. So we go to mechanism, we'll find the 3D contact. It's going to be between this part and that part. Okay, good. And contact properties, coefficient of restitution is 1. We assume it's a frictionless surface, so 0. And then we say okay. And that's pretty much it. So let's go ahead and run it. Let's go ahead and run it and see what happens. So I went to simulation and then run these things. This is finished. Say okay. Let's go and select this file that's created. We go to results and play animation, and let's play it. So this is going to fall. It's going to hit this thing and kind of bounced. Okay, so let me show you again. Let me go back here, change this thing actually to 1, because I want to show you what happened, and run it again. Simulation, run analysis case. When it finishes, that's it. Select this. You have to go to result and play animation. And let's actually make it play over and over and over. There. We can slow it down, by the way. Okay, the point is that I don't want it to go that far because I want stuff immediately after impact. So here, I'm going to put 0.65, 0.65, and for sampling, I'm going to put step size, and I'm going to put 0.005. Now, let's look at these things. Start of output when. So let's say at a time, maybe 0.5. Let's make it 0.5. All the 0.5 all the way to the end. We're going to come back and make some adjustments here. So we say, okay. Obviously, we're going to run it. Wait until it finishes. Good. And select that, go to results, play animation, play it over and over. Okay. So you see, it hit this thing, and you can see that actually coming down, and it's hitting it. So that's good. That's good. Now, close that. Let's do the 2D plot. 2D plot. Now, let me see now. We are going to look at the angular velocity of the floor, the rod. And about what axis? About the x-axis. Angular velocity about the x-axis at plot. And let's see what happens. Before it hits the ground, the angular velocity is 0. You can see that. 0, 10 to the minus 20, that's 0. And then when it hits the ground, it goes to 20.4. And look at what the theory predicted. Theory predicted is roughly 21.26. Now, the other thing is that I want the velocity. For the velocity, what I'm going to do, I'm going to say, okay, we'll keep that. We go back to mechanism. We're going to create a kinematic measure. And for the point, for the monitor point, is that point that I selected. I can do it from the tree, or I can go to the rod and select it from the branch right here. So this is the point that I want to monitor, velocity of that point. Now, obviously, I have to go run it again because I made a request here. So simulation, run it, close. Obviously, this thing doesn't change, but if you click on that, you're going to get edit. I want to add something to it. I want to add that kinematic measurement 1, and that'll be the velocity in the z direction, and then add. So look what happened. This is before impact. So velocity roughly 0.61 minus 0.618, 0.62, which agrees with the free fall. And then when it hits it, goes over here, it gives you minus 1.2, 1.196, and stays like that. So look, minus, what is that? Yeah, 1.2, I get 1.19, and 21.26, I get 20 point something 8. So this is good. Now, what I want to show you is what happens if I go and change that end. So if I go and change that end, where is that thing? It's in rod, right? In the rod, just shaft, that's sketch. Okay. If I go and make this thing solid line and this construction line and exit, I'm going to see a flat end. I have to go run it. So let's go to the monitor or scenario. Okay, we're going to have to run it. What is that? Simulation. Run it. This thing changed a little bit. It's almost 20.7, not much. But then I also want to add that all right, so I'm going to edit the information, edit this 2D plot, and I will add this last item. So it's going to be velocity in the Z direction, add to the plot. Okay, here's what happened. Notice that before I get the correct value, even after it fell down, I got 1.2, almost 1.19 something. But look what happened with that flat end. Free fall velocity is okay, minus 6 point something. But when I go there, I get minus 0.5, minus 0.4. So this should be 1.2, right? So let me show you here. This thing, see that? It says it's minus 0.568. Say okay. Just to convince you, we go back here to that rod. Where is the rod? Here, right there. And I go and use the round edge. This is going to be solid, and this is going to be construction. Yep, exit and run it. So go to the scenario, and we have to simulate, run. This will change, you'll see. Okay. So let me see if it actually worked here. So yeah, so we go here, minus 1.1. You see that? Minus 1, almost immediately after that is almost 1.2. All right, folks. So that takes care of this tutorial. The only reason I call this thing subtle issues because of this end, because theory requires when you use coefficient of restitution, theory requires that there is a unique normal at that point of contact, but and with a well-defined normal, and with that flat end, that's problematic. But with a curved end, there is a unique normal at the point of contact.